Next, we're going to talk about limits at infinity. So I'm just going to jump in with the definition. We say that the limit as x approaches positive infinity or negative infinity of f of x is equal to L if f of x gets arbitrarily close to L as x approaches positive infinity or negative infinity, depending upon which one we were approaching. So this looks like a pretty technical definition. I'm going to break it down. It's actually pretty simple. Really, we can exemplify this by looking at the function f of x equals 1 over x. This is a function that, if you're not familiar with, it's one that has a vertical asymptote or a rip in the graph right here at x equals 0, where the function is undefined. It goes off to positive infinity as you approach 0 from the right-hand side. It goes down to negative infinity as you approach from the left-hand side. We don't really care about that discontinuity in the center of the graph. What we're talking about today is what happens as x itself goes off to infinity positively, or if it goes off to infinity negatively. And in this graph, it looks like as my x values get bigger and bigger and bigger, my y values, my functional values, start getting closer to 0. And that's true from the negative side as well. As my x values get closer and closer and closer to negative infinity, which can never be reached, it's not an actual number, but as they get more and more and more negative, we see that our y values are getting closer to 0 as well. So another way to think about the limit at infinity is to think about the end behavior. Or what happens as my x values get really big or really negative. Another definition that goes along with this is our definition of asymptotes. We say f of x has a horizontal asymptote at y equals c, and this is a line, y equals c, if the limit as x approaches infinity of f of x is equal to c, and or the limit as x approaches negative infinity of f of x is equal to c. In this example up above, we see that the limit as we approach positive infinity is equal to the limit as we approach negative infinity, and both of those limits are equal to 0. So we would say that there's a horizontal asymptote at 0. But for some graphs, the positive and the negative sides aren't necessarily the same value. For example, let's say that we're looking at this function, f of x. So all we have is the graph, we don't have a function. But in this case, we have some squiggly behavior going on in the center of the graph, and we see that as our x values get bigger and bigger and bigger, our y values seem to be honing in on this value of 3. And it doesn't matter that our graph crossed it here locally, because when we're talking about limits at infinity or end behavior, all that we care about is what happens as x approaches infinity, or x gets increasingly large. Similarly, as we see x getting more and more and more negative or approaching negative infinity, we see that our y values are leveling out near -1. So based on this graphical analysis, we would say that the limit as x approaches infinity of this function f of x is equal to 3, because our y values are getting closer to 3. And we would therefore say that we have a horizontal asymptote at y equals 3. We also find that the limit as x approaches negative infinity of this graph, the y values are getting closer and closer to -1, and so we have the limit of -1, and we have a horizontal asymptote at y equals -1. I want to contrast this really briefly with a function that doesn't have a horizontal asymptote. You might think, oh no, none of that was on your screen. I apologize. So we see that the limit as x approaches negative infinity, our function is approaching -1, or we have a horizontal asymptote at y equals -1. I want to contrast that with a function that we're all familiar with, which is a sine curve. So let's let our function g of x equal sine of x. So this is a function that's periodic. We know it starts at 0 when our angle is 0 because it's our y values, and it's going to squiggle back and forth, squiggles back and forth. And this is a function. It doesn't have a horizontal asymptote, and it also doesn't have an limited infinity, because you see that no matter how far we go out, we're always going to bounce back and forth between a y value of 1 and -1. And so in this case, the limit as x approaches infinity for this function, sine of x, it does not exist. I would write does not exist, because it doesn't approach one single value. It just wavers back and forth between a set of values.